Hello everyone, I am Peijin. This is the first episode of a series of data workshop about the low frequency array in the solar and space weather studies. This workshop is supported by Bulgarian Academy of Sciences and the Netherlands Institute of Astronomy and Dublin Institute for Advanced Studies. So in this workshop, I will introduce the observation data of LOFAR and how this data can be used in solar and space weather studies. This workshop is split into two parts. First part is this episode. It's a brief introduction of LOFAR and its applications in solar and space weather. And the second part is about the data. It includes three types of data that I will introduce: the beamformed, the interferometric imaging, and interplanetary scintillations. Each of these sections contain two parts. The first part is the detailed information of the data, and the second part is hands-on session. So what is LOFAR? It is actually a huge set of antennas spread over Europe and centered in Netherlands. It has two types of antennas, namely the low frequency band and the high frequency band, the LBA and HBA. LBA works in the frequency range of 10 to 90 megahertz, and HBA works in the frequency range of 110 to 240 megahertz. The antennas look like this. So with tens of thousands of antennas like this pointing at the sky, there are so much science that can be done with LOFAR. They are divided into 6 divisions, which are the 6 key science projects. The first one is surveys. It's a mission to scan the sky with high spatial resolution. The second one is cosmic magnetism, which cares more about the magnetic field in the universe. And the third one is my area. It's solar and space weather key science project. It studies the solar activities and its interactions with the interplanetary space. And the fourth one is cosmic rays. It studies the radio signal from high energy particles. And the fifth one is transients and pulsars. It focuses on the time varying signals in the deep sky. And the last one is epoch of reionization. It looks in the deepest part of the sky, which is the most far away place that can be reached by the radio telescope, which corresponds to a really early stage of the universe. So before we start on the data, I want to talk about a really long-term discussed topic, which is the resolution. With such an advanced instrument, we are capable of observing the objects at high resolution. But we cannot have high resolutions at the same time. Because of the limitations of data rate and the computational power of the correlator and the storage, we need to make sacrifices on some aspects in order to reach high resolution on a given aspect. For example, if we want high time resolution and high frequency resolution, we need to sacrifice on the spatial resolution, or we need to reduce the sensitivity. And if we want high sensitivity, we need to average on one of these or two of these three aspects. So it's all about balance. And the best part about radio astronomy is its flexibility. We can easily choose what we want. We can determine the observation configurations to achieve, for example, high time resolution, frequency resolution, and make sacrifices on spatial resolution. And also we can easily change the configuration to reach high spatial resolution and make sacrifices on the time resolution and frequency resolution. Starting from beamformed observation mode. As I mentioned, there are so many antenna elements in LOFAR, and for a single element of antenna, the beam shape look like this. As you can see, the beam angle is very wide. The good point of this is the field of view is large, but it doesn't have any pointings, and it doesn't have any spatial resolutions. So with more elements combined together, working in the form of a phase array, it can form a much narrower beam like this. With the antennas inside a station, it can form beams like this. And with more elements counted, such as an array, the LOFAR can form a much narrower beam with much more precise pointings. And this is called tide array beam. So the pointing directions can be determined by the configurations of delays applied to elements in the software correlator. It can form multiple beams at the same time, which means it can observe different directions at the same time. So beamformed data have two type of observations, which is a single beam and a tide array beam imaging mode. For a single beam is quite straightforward. It's just a single beam pointing at a given direction, for example, pointing at the center of the sun. So it's recording the radial flux from the sun. If there is a radial burst, there will be a bright shining blob in the dynamic spectrum. And another type of data product is a tide array beam imaging. As I said, the tide array beam can be programmed to pointing at any direction in the sky, and it can pointing at multiple directions at the same time. So imagine one beam is a pixel. It records the radial flux at one direction, and combining all these pixels, we can form a image. On the right is an example of the tide array beam imaging of the solar corona. And in the center, the white solid line is the solar disk, and each of the dots, it represents a single beam. So there are 169 beams in this image. Representing this image have 169 pixels. So as you can see, the spatial resolution is quite low, but the time resolution and frequency resolution of this observation mode can be quite high. So the resolution of beamformed observation is like this. Time resolution can reach about 10 milliseconds per frame, and the frequency resolution is about 20 kilohertz, with more than 4,000 channels in this frequency range. But the spatial resolution is quite low. In single beam mode, there is no spatial resolution. And with tide array beam imaging, the spatial resolution is about 10 arc minutes. Yeah, it's just 169 pixels, so you cannot expect sub arc minute spatial resolution. So if we want a spatial resolution, we will use interferometric imaging. The spatial resolution can reach about 1 arc minute, even smaller. But in this case, the time resolution is much lower. It can reach about 1/6 seconds, and the frequency resolution is also much lower. We can choose 60 subbands in the frequency range of 10 to 90 megahertz. So this is an example of interferometric imaging of type 3B and type 3 radio bursts. As we can see, we can resolve the shape and even more details in the source. This cannot be done with beamformed imaging. This can only be done with interferometric imaging. Back to the discussion of resolution. As we can see, beamformed imaging is really good at time resolution and frequency resolution, but it's not so good at spatial resolution. Interferometry is very good at spatial resolution, but it squeezes these two aspects, the time resolution and frequency resolution. And if we want to see weaker signals, we need to do averaging. So another type of observation is interplanetary scintillation. It doesn't look at the sun itself, it looks at the remote stars in the deep sky with a line of sight very close to the sun. And there are density turbulences in the interplanetary space near the sun. So this line of sight can be disturbed as a result. From these signals, we can infer the density fluctuations, the solar wind speed from these fluctuated signals. This is an interplanetary scintillation observation. About data access, all the data recorded by LOFAR will be public available after 1 year of data protection period. It's on lta.lofar.eu, the long-time archive. But here is a problem, which is the data size. The data size is too large with the original resolution. Sometimes it took about a few months to download a big dataset, but it turns out there's nothing happening in this dataset. That would be very awkward. So we are working on a local project called the MiniLofar Sun, which is basically creating a downsampled database. So the process is to download the huge observation data with original resolution to a temporary server and do the averaging and labeling and creating the preview, and after that send all these small files to a local server and provide previews and this small size data to user. In this case, the users can look into the preview and the small size data and do some statistical studies. If they find something really interesting, they can use these labels in the small size data to trace back to raw data with original resolution in the long-time archive. This MiniLofar Sun will be ready in a few weeks. So in the following sections, I will introduce the details of different types of the data, how to process, how to calibrate, how to create science-ready figures for your research.